So, here's the big puzzle we need to solve. We all know how heat is supposed to work, right? It flows from hot things to cold things. Your hot coffee cools down in a cool room. It's a basic rule. But a refrigerator, well, it does the exact opposite. It somehow grabs heat from inside its already cold box and dumps it out into your warmer kitchen. So how on earth does it manage to defy the natural order of things? Well, the secret to solving this little paradox lies in one very special substance. You can think of it as a tiny, tireless workhorse, a kind of heat taxi that picks up warmth where we don't want it and drops it off somewhere else. And this is our hero, the refrigerant. So what is a refrigerant exactly? Basically, it's a fluid that has a very specific superpower. It can switch from being a liquid to a gas and then back again really, really easily. And this ability to change its state, its phase, is the absolute key to how it moves heat around so effectively. Let's break down that superpower. When the refrigerant is a cold, low-pressure liquid, it's basically like a dry sponge, just waiting to soak up heat. And when it does, it boils and turns into a gas. Then, on the flip side, when it's a hot, high-pressure gas, it's ready to release all that heat it's carrying, which makes it condense back into a liquid. You see? It's this perfect, continuous cycle for transferring energy. To make this a little more real, let's look at a common refrigerant that's used today, called R134A. Now, just look at its boiling point, minus 26.1 degrees Celsius. I mean, that is just ridiculously cold. This means that even inside your freezer, it's still warm enough to make R134A boil, which is exactly what we needed to do to absorb heat. And bonus, it's much, much friendlier to the ozone layer than the older stuff used to be. So, how does our refrigerant hero actually do its job? Well, it doesn't just sit there. It travels on a continuous loop, a 4-step journey that we call the vapor compression cycle. Think of it like a racetrack for heat, with 4 really important pit stops along the way. And here they are, the 4 crucial stages: compression, condensation, expansion, and evaporation. Our little refrigerant is about to go through a major transformation at each and every one of these stops, so let's follow its journey step by step. All right, our journey starts at the compressor. This is the heart of the whole system. It's that humming sound you hear when your fridge kicks on. What it's doing is taking that cool, low-pressure refrigerant gas and squeezing it hard. If you've ever used a bicycle pump and felt it get hot, you know exactly what's happening. The compression crams the molecules together, which skyrockets the refrigerant's pressure and its temperature. Next up, this super hot, high-pressure gas gets pushed into the condenser coils. You know, those black, snake-like coils you sometimes see on the back of an older fridge? Because the gas is now much hotter than your kitchen, the heat naturally flows out of the coils and into the room. And as it sheds all that heat, it does something amazing. It condenses, changing from a gas back into a high-pressure liquid. Okay, now for what is honestly the most magical part of the whole process. That high-pressure liquid is forced through a teeny tiny little nozzle called an expansion valve. This causes a massive instantaneous drop in pressure. If you've ever sprayed an aerosol can and felt the can get cold, you've experienced the exact same principle. That sudden drop in pressure makes the refrigerant intensely, incredibly cold. And for the grand finale, this super chilled, low-pressure liquid now flows through the evaporator coils, which are inside the fridge. Because it's now way colder than your milk and vegetables, heat naturally flows from the food into the refrigerant. This incoming heat is more than enough to make the refrigerant boil and turn back into a gas. And in doing so, it has effectively stolen the warmth from inside your fridge. And from there, the gas just heads back to the compressor and boom, the whole cycle starts all over again. Now, to really get why this works so well, we need to take a quick detour and talk about 2 types of heat. First, there's sensible heat. That's the heat you can actually feel. It's the energy that changes something's temperature. But the real magic here is something called latent heat. This is the hidden energy a substance needs to absorb just to change its state, like the massive amount of energy it takes to turn a pot of liquid water into steam. The refrigerant soaks up a ton of this latent heat to boil inside the fridge, pulling huge amounts of warmth away without its own temperature even changing. That right there is its secret weapon. You know, this whole cycle isn't just some clever piece of engineering. It's actually dictated by the fundamental laws of physics. To really understand why your fridge works, we have to look at the universe's official rulebook. And this is one of the biggest rules in that book, the second law of thermodynamics. Now, what that fancy sentence really means is that there's no such thing as a free lunch. You can't have a 100% efficient engine. You will always lose some energy along the way, usually as waste heat. You can just never break even. And that brings us right back to our refrigerator. The second law is telling us that moving heat from a cold place to a hot one, which goes against the natural flow of the universe, is not free. It costs something. It requires an input of energy. And that's the work being done by the compressor, powered by the electricity from your wall. You have to pay an energy toll to bend the rules of heat flow. So we know we have to pay this energy toll to make the whole cycle work. But how do we know if we're getting a good deal for our money? Well, that's where we get into measuring the real-world power and, more importantly, the efficiency of these cooling systems.
So in the HVAC and refrigeration industry, you'll often hear a strange-sounding unit of power, the ton of refrigeration. It sounds weird, I know, but it has a very specific meaning. It's the amount of cooling power you would need to freeze 1 US ton of water into solid ice over a 24-hour period. It's just a standardized way to talk about cooling capacity.
To put that in terms you might be more familiar with, 1 ton of refrigeration is equal to about 12,000 BTUs per hour. Now, BTU stands for British Thermal Unit, and you've probably seen that number on the side of a window air conditioner. It's simply a measure of how much heat that unit can pull out of a room in 1 hour. But raw power is just one part of the story. The other, arguably more important part, is efficiency. And for that, we use something called the coefficient of performance, or COP. It's actually a pretty simple ratio. It asks, how much heat did we successfully remove, divided by how much work or energy did we have to put in to make it happen? You know, the absolute easiest way to think about COP is as the miles per gallon for your fridge or your air conditioner. That's it. A higher COP means you're getting more cooling punch for every single watt of electricity you have to pay for. It's the ultimate report card for how efficiently your appliance is running. And just like with MPG, higher is always better. So when you boil it all down, the science shows us that cooling isn't about creating cold, it's about moving heat. And moving heat, as we've learned, always costs energy. This leaves us with a really critical question for our future. As our world gets warmer, the demand for cooling is only going to go up. So how do we meet that need efficiently and sustainably? That right there is the challenge that's going to define the next generation of cooling technology.